Hello everyone, welcome back to the tutorial for mechanical vibrations. Today we are going to continue on the free vibration of single degree of freedom systems, but for a different case. So in the previous tutorial we worked on the system that has no damping, but today we will be talking about the case that we have damping in the system. Right, so let's begin. So imagine that we have a single degree of freedom system like this one. So the most simple case is when we have a spring and a mass in the system. So this is the case that we studied before, and we noticed that the equation of motion is something like mx double dot plus kx. So now we have a viscous damping in the system for today's examples, which is here, and C is the damping constant, and the force regarding the damping is Cx dot, basically, right, which is equal to 0. So it's a second order differential equation. To solve that we need two initial conditions, x dot naught or x dot at 0 and also x at 0. These are the two initial conditions as we had before. So in this system we need to know some definitions basically for studying the system. First of all, we know that the undamped frequency or undamped natural frequency omega n is equal to square root of k over m. We also have basically a damped natural frequency which is omega d, and in order to find that we need to know something called zeta, and zeta is equal to c over c critical. So zeta is the damping ratio, and what is the c critical? C critical is the critical damping, and in fact C critical is also a function of the parameters of the system, which is equal to 2m omega n, and also you know omega n is here, so it's a function of k and m, right? So omega d is equal to 1 minus zeta squared times omega n. So as you see, omega d is a little bit smaller than omega n, so it depends on how the value of zeta is, then we can have omega d if the system has a harmonic motion, right, which is the basically the case that we have the damped frequency. So remember, for this equation, in order to find the response of the system, we need to basically solve the second order differential equation and apply the basically the initial conditions. But something that is important to know is when like zeta has a special value. So basically the damping ratio could be equal to 1, could be greater than 1, or could be smaller than 1. So basically for smaller than 1 we call it the underdamped system. For zeta greater than 1 we call it overdamped, and also for zeta equal to 1 we call it critically damped. Right, so these three cases give us different responses for the system. So we quickly want to review what's going on for these cases. So basically when we have like the time response of the system, if this is t and this is basically the like xt response of the system, for a like specific initial condition, for example at x naught, the basically the underdamped system give you a sort of harmonic response with a logarithmic decaying, and however this is basically when zeta is less than 1. For the case that we have basically a critical damping in the system, we have something like this, right? So this is for the case that we have zeta equal to 1, and for the case that we have a overdamped response, the response is something like this, right, with a slower decay than the critical damping. So basically this is zeta greater than 1, and as you noticed, for the case that we have a critical damping, we have the fastest time to get into 0. So this is a very important consideration for the design. So we need to design the damping of the system to be equal to the critical damping, and we know critical damping is a function of the function of m and omega n, or the function of m and basically k, right? So basically C critical is also equal to 2 m omega n, as I wrote before, or 2 square root of k m, right? However, for many cases we deal with a system that we have a underdamped condition, which means that zeta is less than 1 and we have a omega d equal to 1 minus zeta squared omega n, right? This is the case that we have underdamped, and as you noticed from my drawing, the response is harmonically decaying to 0, and this is something like a logarithmic decay, which showing that how the amplitude is going to 0, and the response is something like a combination of a basically an exponential term and a harmonic term. Basically xt is equal to e minus zeta omega n t times a cos omega d t plus b sine omega d t, right? So it is a combination of a harmonic term and a decaying exponential term, and depending on the initial conditions we can find a and b, right? So this is the summary of a system with a free vibration, and basically there is no force, and we both have a damping and a stiffness in the system, and we are going to have a couple of examples today and see how we can deal with these systems. So let's begin. Okay, so this is the first example we have for today, and as you can see from the problem statement, we have a spring mass damping system, which means that we have something like this, right? So we have a viscous damping C, stiffness K, and the mass M, and we know the value of M, K. So the question for part A is asking find the critical damping constant, which is C, C or C critical. And in the second part, we want to find the natural, like the damped natural frequency when C is half of the critical damping, and also the log decrement or logarithmic decrement. I'll discuss that later on. So let's study part A. So the system is asking for the critical damping. Like I said, critical damping is like a parameter depending on the stiffness and the mass. So C critical is equal to 2 square root of K times M. For this case, we know both K and M, so we can do the calculation, which gives us 1000 Newton second per meter. So this is the critical damping. So this is very simple. We can also use the formula we have for basically based on omega n, gives us the same value. So it is equal to 2m omega n. And what is omega n? Omega n is basically a square root of K over M, right? So we can simply find that. Okay, so that's it for part A. Pretty simple, right? So let's do the second part, which is looking for the damped natural frequency. So what is the damped natural frequency? The damped natural frequency is omega d, and I will show you what it means, which is equal to 1 minus zeta squared omega n, and it is equal to 1 minus zeta squared times square root of K over M. So what is zeta for this case? So in part B, we notice that C is equal to C critical divided by 2. So we can simply find zeta based on this definition. In fact, zeta is equal to C over C critical, which is C critical divided by 2 divided by C critical, which is 1 over 2 or half. As you see, zeta has no dimension. Why? Because it is a ratio of damping, right? So we can simply plug in everything in the above equation. As you see, we know zeta, we know K and M. So if we do so, we have omega d is equal to 8.66 radian per second. So what is basically the damped frequency? Just imagine if we have the response of a underdamped system. And why underdamped? Because zeta is less than 1, right? So we have an underdamped system. So the response, if we plot it versus time, is, and given we have an initial amplitude or x naught, should be something like this, right? We have a decay in the system. So in fact, omega d is the, basically, if we take this as Td, or the basically the period of damped vibration, So omega d is the frequency of that, and it is like this, and this is another TD. So we know that omega d is 2 pi over TD, right? This is what we know from the definition of frequency and period, right? Omega is equal to 2 pi over T, right? So this is how we can imagine what omega d is. Okay, so that's for the part B of this problem, and now we can continue and discuss the log decrement or logarithmic decrement in the next slide. So in the last part of this problem, the problem is asking for the logarithmic decrement. So let's first define what the logarithmic decrement means. Again, I want to plot an arbitrary response of a underdamped system, which is like this. So if we look at the slope or how the amplitudes are decaying, it is like a exponential sort of decay. So in fact, this curve follows E minus zeta omega n t, and this part is the harmonic part, or the cos and sine function combination. So the logarithmic decay means the ratio of basically how these amplitudes are decaying. So in fact, you can define it as the logarithm of the ratio of any two successive amplitudes. So we can use this to find that, or this one and that one, or that one and the next one. So in fact, for like based on the definitions, we can define delta, the log decrement, equals to the basically the ln x1 over x2, or you can use other x1. So what is x1? x1 is here and x2 is there. So we can also use x2 and x3. So you can somehow combine these two. And what is like important about the logarithmic decay, it is when we have basically the response of the system, we can use the amplitude values, for example, if it is from the experiments or so, and then use that to estimate the damping behavior of the system, right? So that's why it is important to know the logarithmic decay. And in fact, the function or the formula for delta is equal to 2 pi over omega d times C2m. This is the formula we have based on the damped frequency, damping constant, and the mass of the system. So for this system, we have everything. We know omega d from before. We have C, which is equal to C critical divided by 2, and 2m. So we can simply find that as 3.627. And there is no basically dimension for that or unit for that because it's the ratio, right? So as you see, we found how basically the amplitudes are decaying as the system goes forward or as the time passes. So imagine the case that you have this curve from the experiments, and then you want to estimate what is the damping constant of your system. So you just pick 2 points, find the ratio, and then get the ln and find delta, and then put that value into this formula or set that value equal to this formula. You know omega d again from the experiment results, you know the mass, so we can estimate the damping of the system if we suppose that there is a sort of equivalent viscous damping in the system. I hope you got the point of using the logarithmic decay for estimating like your system basically damping or equivalent damping constant. Okay, so that's it for this example. Now let's go to another example which deals with a torsional system and see how we can basically solve for that case as well. So let's do that. Okay, so this is the second and the last problem for today. So let's just go over it and see how we can solve that. Okay, so in this problem we have a torsional pendulum, and I will show you like schematically what a torsional pendulum may look like. And we know the natural frequency when vibrating in vacuum. When we say vacuum, it basically means that there is no sort of damping or for simplicity there is no sort of air resistance or liquid resistance. So imagine we have like a shaft connected to a disc, and the disc is rotating with the angle of theta. And so this is some sort of simplification we can have for a torsional pendulum, or you can have other cases, or you can have a, I don't know, well, this like rod has no no mass, it just has a stiffness, or you can have another case that there is a sort of torsional pendulum, something going this way, anything you can imagine that the system is under torsion or sort of rotation, right? And now you have, for this case, we have the mass moment of inertia. So let's just use J as the mass moment of inertia for this case. And it says it's a disk, so we don't use this system. We can have this system I draw here, and we know J for the system. And then the system is immersed in oil, right? Which means that there is a sort of viscous damping, and the natural frequency changes to a smaller value. So this 180 is actually our omega D. Now we need to find the damping constant C due to the oil, or placing the system into oil. So what happens to the system? Here we have omega N equal to basically K, the torsional basically stiffness over J. Now the system goes or immersed into an oil bath, something like this. And this is oil, sorry for my drawing. And then we have a sort of viscous damping added into the system, and that's why we need to calculate like the damping constant for this system. So in that case we have omega D, right, which is equal to 1 minus zeta squared omega N. Okay, so now the system or the problem is looking for the damping constant C if well, we have this sort of behavior. Also, it says that if the disc is like placed in oil and an initial displacement of 2 degrees is given, find the displacement at the end of the first cycle, right? So we have a sort of initial condition in the form of displacement. Now we want to see what is the displacement at the end of first cycle, or theta t, when basically we have first cycle, or t equal to the period, right? So let's see how we can find this. I hope you understand the problem, and now we can continue on finding the conditions and the responses. Okay, so what we found here for the first case, we found out that omega n, which is equal to k over j, for this case is equal to 200 cycles per minute. This is something given, right? But remember, for omega, as I mentioned in my previous video, we always use radian per second, so it has to be converted to that. So how can we do that? Just times 2 pi over 60, right? 60 seconds, and each cycle is 2 pi radian, which gives us 20.94 radian per second. So this is how we can find the natural frequency of the undamped system. Then for the damped system, we have basically 180 cycles per minute. So we time 2 pi over 6 or 60, which gives us 18.85 nearly radian per second. As expected, the damped frequency is basically smaller than the undamped frequency, right? So we have everything. We know that basically zeta is equal to C over C critical, right? Or we know this is C over C critical, and C critical is 2J omega N, right? We have a torsional system, so we use J instead. So let's see what we have here. We have omega D equal to 1 minus zeta squared times omega N. Then by basically substituting this, we can simply find zeta. So as you see from here, we can find zeta because we have omega D and omega N. It is just a sort of, simplification, which gives us the value for zeta. You know how to do that, right? Because simply If we simplify that, we square the two sides. We have omega d squared equal to 1 minus zeta squared omega over omega n squared. And then, in fact, zeta can be simply found as 1 minus omega d divided by omega n squared. And we expect a positive value less than 1 for zeta. So if you're doing the calculation and you got a number that doesn't make sense, then you need to recheck your calculation. So if we do this, we can find zeta as 0.436, and as expected, it is positive and it is less than 1, right? So let's continue. So what we found here is basically zeta is equal to C over C critical, which means that C is equal to C critical times zeta, and we know that basically C critical is equal to 2j omega n. So C is equal to 2mj, or sorry, I have a tiny mistake, so I need to use j instead of m. Let me do that again. Yeah, so we have 2j omega n times zeta. So we know j, we know omega n and zeta, so we can find 3.652 Newton meter second per radian. As you see, it's basically a sort of torsional damping constant. That's why we get this unit for the system, right? So we will be able to find the first part of the response or the solution for the problem, which was looking for the damping constant. So we found C. Now we need to move to the second part, saying that if we have theta not at 0 or theta naught equal to 2 degrees, what is like theta at the first, like t equal to basically the first period, right? What is the displacement of this system when we have basically the first period of motion ending, right? So remember, one important consideration for this case is we always have to use radian. Again, if you have something in degrees, you have to convert it to the radian. So remember, theta naught or theta at 0 is equal to, if we just do some manipulation and you know how to convert degrees to radian, it is equal to 0.03491. How can you do that? I always use a simple formula, which is degree over 180 equals to radian over pi. So pi is 3.14 or something. So you can use this formula for your conversion, right? So we know that there is no initial basically velocity. So theta dot naught equal to 0, or theta dot at 0 is equal to 0. Just keep it in mind, right? I hope you got this point, right? Okay, so with these assumptions and this condition, we need to find the response of the system. So as I said at the beginning, theta t is equal to E minus zeta omega n t times, we can use this formula as A cos omega dt plus B sine omega dt. And don't worry, the functions for A and B are available, so you don't have to basically repeat or find them by yourself. You can simply find them in the textbooks, which are actually available for basically this A and B. For A, it is equal to theta naught, and for B is equal to theta dot naught plus zeta omega n theta naught divided by omega d, right? So if we have a translational motion, we can use x instead. So as you can remember from the previous slide, we had theta naught in our system, but theta dot naught was 0. So we can find the response of the system as theta t equal to E minus zeta omega n t times theta naught cos omega d. Sorry, I may have to rewrite it again. So that's it. We have cos omega dt plus zeta omega n theta naught divided by omega d sine omega dt, right? So this is the response of the system. So we need the case that t is equal to tau, and tau or tau d is equal to 2 pi over omega d, right? So everything is clear. We know omega d, right? We found it already, and we can simply find tau d, which is the period of the damped vibration, and if we plug in t equals to tau d, we can find the amplitude, right? So let's see how it works. So for this system, as I said, we know everything as we know omega d, and therefore we can find tau d, the period of the damped vibration, equal to 0.333 seconds. So if we know td or tau d, and then we have theta t equals to e minus zeta omega n t times theta naught cos omega d t plus zeta omega n, basically theta naught divided by omega d sine omega dt, right? So we know everything, we just need to plug in everything. So we use omega n, we know zeta, we know omega d, and we only have to plug in t equal to tau d or 0.333 seconds. So if we do that, and I don't want to repeat all this calculation, we can find theta at tau d, which is the displacement at the end of the first cycle, equal to 0.00166 radian, which is equal to nearly 1 degrees, right? So in fact, it means that if we give an initial displacement of 2 degrees to that disk, then it for one period it displays for 0.1 degrees, right? So in fact, we can plot it something like this. And why we have this like going down? Because the slope, which shows the velocity at the beginning, is equal to 0, right? We call theta dot at 0 equal to 0. So this is 2 degrees, the theta. So after one period, it is basically the displacement is 0.1 degrees, right? I hope you got the point of this problem. So for now, we studied both the undamped and the viscous damped case, and we solved a couple of examples for such free vibration of the first degree of freedom systems, and we are going to have a couple of more examples in the future. I hope you enjoyed the video, and stay tuned for the next videos.